Continuing with question number 8. Says, to prove that the diagonals of a parallelogram bisect each other, Xavier first wants to establish that triangles APD, so APD, and CPB are congruent. Which criterion and elements can he use? Okay, so here we obviously want to use the properties of parallelograms, which are found in chapter 7. Let me see what lesson 7. (7)(2). That would be helpful. But then we also want to use the side angle, the triangle congruence from sections 5.3, 5.5, and 5.6. So again, that's 7.2 for the properties of parallelograms, and then 5.3, 5.5, and 5.6 for the triangle congruence theorems. Now, with the properties of parallelograms, the only one that we cannot reference, that we cannot use or consider, would be, let's see, where is it? Theorem 7.6, parallelogram diagonals theorem, which states that the diagonals bisect each other. Since the purpose is to prove that the diagonals bisect each other, we have to operate on the idea that we don't know yet that DP and PB are congruent and AP and PC are congruent, that these cut each other in half. So that's beneficial, because if another version of this question could say, which theorem would help prove that these two triangles are congruent, so it would be one of these, you would already be able to eliminate side angle side and side side side. Since we only know that that these two sides AD and BC are congruent, and again we cannot rely on the knowledge that the diagonals bisect each other, well then we can't use these two theorems because they have two sides, right? You need two sides in the included angle or all three sides. So we would only be able to have one. Alright, so then in the event that this is a multiple choice question, A and B, they're out of the running because they use side angle side. So that means it has to be one of these two. So we have to consider, well, since we're talking about angle side angle, remember those names are not just in random, they're just not, the letters aren't just assigned because it sounds good. This is actually the pattern. So we have the side and the included angles, because any triangle has, like any side of a triangle is closed off by two angles. We have angle ADP over here and DAP. Alright, so we would need, if angle side angle is going to be used, is these two corners, these two vertices A and D of the triangle. And then for B and C, the angle at vertex C and the one at vertex B. So that's really the one that we would use. Looking at the two options, the one that would make the most sense would be option D here. Alright, because of angle, side AD and BC, and those are the given sides with the adjacent angles. Why wouldn't this one work? Well, because they're saying DP and PB, which are the two sides of the diagonal. So again, we don't know that those pieces are congruent. We don't know that this diagonal DB is being cut in half. So this option would not make sense. Again, that's in the multiple choice context. If it were in a, hence, select all that apply, then you have to look at all the different, possibilities of what could work. Because, angle side would also fit. Because if we consider the vertical angles in the middle here, well then you would have, put the markings. You could have angle, and then the side. So it could ask it in that form. All right. So fortunately, this is not one that doesn't require much work to be shown. I would, include the labels here. And moving on to 9. Okay. Once again, 9. This page is pretty much using those three sections: 5.3, 5.5, and 5.6. You need to, again, know what these mean, and also, how they are presented, how to identify them. Because, again, they're not necessarily just names put together for the sake of having a, nice little acronym. They describe the pattern. Alright, so question 9. It says, which statement is sufficient evidence that the triangle DEF is congruent to ABC? Alright, so again, here they don't mention the theorems, the angle, side angle, hypotenuse, like they don't mention those congruence theorems by name, but that is effectively what you need to keep in mind, like for this one. So like here so remember, that's also important to keep in mind is the names that are given here. So the names D, E, F, and A, B, C, again, those are not just put together because they're in alphabetical order. That tells you which pieces go together. They discuss the corresponding parts. So for example, if the two triangles are congruent, then the angle with vertex A, which is this angle down here, that one would be congruent to the angle at vertex D, this one over here. And then B goes with E, and then C goes with F. Right, B with E, C with F. So that's important to keep in mind because then that can point us to the statement, the correct group. So sufficient evidence that the two triangles are congruent. Here, if we notice, they mention two sides. Do they fit the pattern? AB to DE. First two letters here, first two letters there. So that's how we can that's how we can tell which segments go together. The two letters at a time in the same position of the names. Alright, so that checks out. BC to EF checks out too, but there is no theorem here that only involves two sides. We need that third piece of information. I mean, I guess technically B only uses two sides, but there's nothing about right angles here, so that wouldn't work. Right here, this one matches up all the corners, all the vertices. D to A, okay, that checks out. B to E, and C to F. However, nothing here involving all three angles, only two at most. And then all the angles being congruent doesn't prove congruence because that like two angles prove similarity. So that one doesn't work. So again, you have to keep reading through and seeing which one of these matches up, which one has the correct criteria. So between these two, one thing to point out here is that notice in this case it says there is a sequence of rigid motions that maps point A onto point D. So keep in mind the way that these things are, written, that they're, because again, the points mapping onto each other, that just means that point A would go on top of point D, but you have to ask yourself, does this necessarily mean that the angles are congruent? Because let's say I have two angles. Right, let's say we have these two angles, and we put one, like we put the course according to the theorem. We put we fold this one over and rotate it so that they're layered on top of one another. If the points landing on matching up, let's say this was point A and the angle looks like that, and then we put, again, it goes on top of point D, so point D I'm going to label it in red, but then the angle at D right, so again, that doesn't necessarily mean that the angles are going to be congruent. So this one kind of leaves, like, again, keep in mind, read the questions carefully for reasons like that. And number 10 over here. Number 10, it's a proof. Now for proofs, remember you're going to have those should be drag and drop, or maybe they'll have like little drop down menus. I don't know. I don't get to see the test, so I can only theorize what the question is going to, how a question like this is going to show up. So some things to keep in mind is how proofs typically go down. So something to always keep in mind is that you're given information. Sometimes, see right here we have AE bisects BD and then AB parallel to DE. Many times if you have more than one given piece of information, you'll find them in the first statement, but sometimes, again, there's a comma right here, so it's two separate pieces of information, and you'll notice only the first half is mentioned here, the second half is not in the same box. However, regardless, the given information is typically at the top of the whole thing, right? So you can use that. If they ask you to fill out the entire proof, well then use this information to kind of to help you out. Because again, you don't have to, with the proofs, you don't have to fill them out in order. You can start from the bottom, work your way back up, start from the top, work in the middle, and whatever you spot. Use since you're not gonna have to do it from scratch, use the things that are given to help you connect the dots. So for example, right here we can see, well, this is at the top, so logically you can already say from the options that you have, from the options that you have down here, the one that makes the most sense to go in box 1 would be given. Because when solving any problem, you start with what you know, and from that you see how the dots connect and what other things you can conclude, what else you can deduce from that given information. So since that's in the given information, well, given is the thing that makes most sense here. And look, we can even see here, oh, this reason is given, so we say, well, what other information are we given? Oh, okay, so then that must go here. Alright, so we're able to narrow it down that way. Now as far as these other ones, that means you still have 4 pieces of information, so what could go where? Well, remember, you don't necessarily have to consider everything, break it down. This one, the reason given is definition of a segment bisector. So if it's talking about a segment. So if we look at again, we've already determined where this one goes and where this one goes. So we have A, C, D, and F. Now, definition of a segment bisector. So does it make sense to consider these angles here? No, not really. So we know, okay, well, it's got to be A or F, and it's got to be one of those two. And then down here, alternate interior angles, same deal. We have, the 2 angles here, so then that means it's likely going to be C or D. Now, do they both fit? Well, that's also something that you have to keep in mind, right? Because if we look, in the alternate interior angles, again, that takes you back to chapter 3, section 3.2, I believe it was. And you can say, well, I have my parallel lines, and then AE is a transversal, BD is a transversal, so angles A and E, okay, those appear to fit the definition of alternate interior. If you're not sure, go back and check. And what about B and D? Well, they also seem to fit, the definition. So you could say, if you ultimately you don't know, take a guess. But remember, you can also use this piece of information. Since you know you're supposed to use angle side angle, see which one fits the bill. Right, considering with a segment that, like option 3 here, which angles make sense. You can also use this one, since ACB, the angles here in the middle, vertical angles, are used, and keep that in mind as far as which one is going to fit the pattern. Is it going to be A and E, D and B? Which one's going to fit for angle side angle? Okay, that's question 10. For question 11, here we want to go to section 6.5, theorem 611. Theorem 611, which is your triangle inequality theorem. The sum of the lengths of any 2 sides of a triangle is greater than the length of the third side. So one thing there is that, again, maybe it's not going to be multiple choice. What I can see them doing here is they give you the x, they give you the less than, greater than, and they put some text boxes on either end, and you have to put in the numbers there, because it's going to have to be a range. If you're given 2 sides of a triangle and you're asked to determine what the possible length of the third one could be, it's not going to be one value, it's got to be 2, it's going to be a range. Alright, so it's really straightforward. All you got to do, take the two numbers you have, add them up to get the max, subtract them to get the minimum. Literally all that there is to it. There's a good example in section 6.5. Let's see, that's exactly like this problem. Let me go and find it right quick. Let's see here in 611. Example 5, right after where the theorem is covered in the book. So again, section 6.5, theorem 6.11, example 5. That's where you're going to answer this one, or you're going to find another example for that one. Number 12. This one is also in the same section, 6.5, but this one relies on theorems 6.9 and 6.10. And example 4 is a pretty good one to use there. Now, in the textbook, they only talk about it in 1 triangle, but it works when you're talking about 2. Because if we look here, we could say that, well, if these triangles are to be congruent, they would be congruent by side angle side, because we have FE congruent to FG, and both of them share FH, so they have two sides that are congruent, and then you have the included angles here, so side, angle, side, side, angle, side. However, since the angles are not congruent, well, then that tells us there's no way that these two, that the triangles are going to be congruent. So is there a relationship that we can establish? Well, the theorems tell us that when an angle, which in a triangle, whichever angle is bigger will be opposite of the longer side. And it works vice versa. The longer side is going to be opposite the larger angle. So from, again, looking at the measures, from there we should be able to determine which of these two sides should be bigger or smaller. Alright? So it's not that no conclusion can be made. There is a conclusion to be made. Just have to look at the numbers and from there sort it out. And if you're not sure why, think of it like, think about when you have an angle. If I have an angle, what happens to the distance between the two endpoints if they get wider? Let's say we take this side and we make it wider. So are these 2 points, again, let's pretend that the blue is the same, that the blue segment here, let this thing focus. Okay, sorry about that. Let's say that the blue segment here is the same as the red one, just opened up wider. So are these 2 points closer together or are they farther apart? So what happens to the distance with regards to the angles measurement? So on to question 13. So question 13 is dependent on your vocabulary knowledge here. Now, there's a lot of vocab, and you gotta know a good chunk of it there. Alright, so centroid, orthocenter, circumcenter, and incenter. Orthocenter is the one I think that is not going to be there much, but either way, it's good to know just in case. Centroid and orthocenter, you want to check those out in section 6.3. Circumcenter and incenter, section 6.2. Centroid has theorem 6.7 associated with it. Orthocenter doesn't have a theorem, but it's the terms that come in handy here are the altitude of the triangle. That's how we get orthocenters. There's a couple of vocabulary words that are associated with these, not just the words themselves, but there's words that go along with them. For example, the centroid. The centroid is identified by finding the median of each side. So what's the median? Let's say we have a triangle. The median starts at one of the 3 vertices and goes to the midpoint of the opposite side. So this segment here, if this is a median, it cuts this segment AB right down the middle. So if we do that for each side, where from A to this point and B to this point over here, if each of those cuts their respective sides in half, then the point of concurrency, the point where the 3 come into contact, that's going to be your centroid. Alright, so what's the orthocenter? So the orthocenter is determined by the altitudes. So what's an altitude? If I have a triangle and I make a segment from one side perpendicular to the other, it's not necessarily going to be splitting this side, into equal parts or anything like that. It's just that it's perpendicular. So if we're starting at one vertex perpendicular to the opposite side, that's an altitude. Again, if we have the altitude from this corner to this side, or this corner to that side, those 3 altitudes will come together at some point, and that's going to be your orthocenter. Circumcenter. Now for this one, you need the perpendicular bisectors of the sides. So not the angles we're just talking about. So for that one, let's make a quick little sketch. I have some paper here I can use. And let's say I have a triangle. Alright, so if we take some triangle and we find the midpoint, and I'm just kind of eyeballing it here. So let's say we find the midpoint, and then we make a line or line segment that is perpendicular That's your perpendicular bisector. So again, if we make one at each of the three sides, there's going to be some point where they meet somewhere along here. There's going to be some point where they meet, and that's what we call the circumcenter. Alright, and then finally your incenter. If we, again, let's make a quick sketch over here. Your incenter is dependent on the angle bisectors. So instead, so again, this time we're starting at the corners, and let's say we determined where the angle bisector passes through. Again, just eyeballing it here. So let's pretend this is the angle bisector. So this angle gets split right down the middle. So if we find the angle bisector from this corner and that corner, the segments all come together, and that's where your incenter is. Okay, so now these points, they have additional relationships to either the sides or the vertices. Circumcenter is the key here. The circumcenter is equidistant from all three corners. So if we find let's bring this back in. And let's just assume the other perpendicular bisector is about right there. And then the third one. And if we found all three, right? So put the tick marks there. And then our 90-degree angles. So on this point right here is your circumcenter. So if we were to connect that circumcenter, that point right there, to that vertex, the vertex on the bottom left and the one on the bottom right, then these three segments, the ones in green, would all be the same. The circumcenter is equidistant, the same distance from the three vertices. And again, refer to the notes in section 6.2 and 6.3 so you can review those relationships. Alright, question 14. Some important vocab here. Gotta know what complementary and supplementary mean, section 1.6. And you also need to know these vocabulary words, congruent, acute, and obtuse, from section 1.5. Alright, because it tells us in triangle PQR, angle Q is a right angle. Select all the statements about angles P and angles R that must be true. So again, something else that helps us here is, well, we know it's a right angle, so it's a right triangle. So make a quick sketch. Doesn't have to be perfect, just a good visual aid. Right? If you're making sketches, don't worry about making them like picture perfect, just something that you can visualize. So we know that since angle Q is a right angle, this is a right triangle. So that gives us information that we can use to determine what's always going to be true. And keep in mind, it doesn't say what could be true, it says must be true. Read the questions carefully. So something that helps here, in addition to your vocabulary words, is corollary 5.1 from lesson 5.1. That one's important for the angles for C, D, and E. Alright, so picture is important. Why? Because again, you got to pay attention to where these vertices go. Since Q is the right angle, that means Q has to go down here, P here, and R there. Wait for it. There we go. So again, P up here, Q has to be the right angle, and then R has to be on the bottom. Again, the remaining vertex. So then from there, we have to ask ourselves, well, what do these terms mean? Well, complementary means they add up to 90. Supplementary means they add up to 180. So we know one of those definitely is not going to be true, because what do we know about the three angles of a triangle? Right? They add up to 180 degrees. All three of them add up to 180 degrees. So ask yourself, does it make sense for these two to be supplementary if all three of them add up to 180? And what does complementary mean? If you recall from one of the previous questions, complementary means they add up to 90. Well, we know the three angles add up to 180. We know that since angle Q is a right angle, that it measures 90 degrees. So then, again, how many degrees do we have left? Does that make P and Q complementary? Alright, and then from there, congruent, acute, and obtuse. Now, congruent means the angles are the same. Acute means they are less than 90. Obtuse means they are greater than 90. So again, consider what we know about the angles of a triangle, and you'll know which of these answers are correct. There are two of them. Alright, question 15. Question 15. Uh-oh. glitch at the beginning of question 15. Anyway, picking up where we left off. So now here they're telling you point D is the centroid. So again, recalling your knowledge of what centroids are and how that all kind of connects. We know from section 6.3 theorem, the centroid theorem, theorem 6.7, and that's what gives us some of the information here. Now that formula I don't believe is going to be included in your formula sheet that you're going to have access to, so it's one that you want to keep in mind. So and you really got to know how it pieces together so that you don't confuse which segment is which. Remember, the figures aren't necessarily drawn to scale, so you have to be mindful of you know where you're starting from. So the theorem states that from the vertex to the centroid, so vertex to the centroid, this distance is going to be 2/3 of the entire segment here, the entire median. Alright, so from C to D, that's 2/3 of the way for E, from C to E. So that's how we can start setting up our formulas here. Now, if you're using the book, it only gives you the one relationship. So if we're using the paper, or the figure here, we know that CD is 2/3 of CE. Now you might say, well, how does that help me if they give me DC, or I guess here they put DC, but DC and CD same thing. All right, they gave us DC and ED, which is this piece over here. So again, what good is that if I don't have that? Well, again, you got to keep in mind, think logically. If this is 2/3 of the entire distance, well, then we can reasonably conclude that ED is 1/3. Right, we have 2/3 from C to D, so where's the remaining third? Well, that remaining piece. So ED would be 1/3 of CE. But again, that doesn't necessarily relate DC, CD to ED. So what can we do with that? Well, if this is 2/3 and this is 1/3, well then CD and ED, then CD must therefore be twice the length of ED. Alright, so you want to remember these three. So again, from the vertex to the centroid, that's 2/3 of the entire median. From the centroid to the midpoint, that's 1/3 of the entire median, and which means that from the vertex to the centroid is twice the length from the centroid to the midpoint. And so that's how you set this one up. Alright, I'm trying to speed run here. I know this is already the third video, and the other ones were like 20 minutes long, so I'm trying to speed run. Alright, JKM, and follow your vertices, JKM. So ultimately, what is the measure of this angle outside? So here we want to remember section 5.1, theorem 5.2, example 3. So again, lesson 5.1, theorem 5.2, example 3. So 5.1, pull that up over here. That's your exterior angle theorem. Your exterior angle theorem. And the example in the book is actually very similar to the one that you see in the review here. Alright, so it simply states that the angle outside the external angle is congruent to the sum of the remote interior angles. Remember, it has to be the angles that are not adjacent to it. Right? This is the angle adjacent to it, so this is also an interior angle. So we want what are called the remote interior angles, which are the two angles inside of the triangle that are not next to the one on the outside. So again, this one is equal to the sum of these two. That'll help you find the value of x, which you can then plug into 5x minus 3 to find the value. Let's actually jump back. I didn't give you the answers for 15 and 16 since those involve work. Let me give you those. For 15, jumping back to that one, 51. And then over here, it's supposed to be 1 57. Alright, moving on. Alright, 17. So as a carpenter builds a frame from 2 6-foot long boards and 2 8-foot long boards, given these side lengths, how can the carpenter ensure that the frame is a rectangle? So here you're going to want to refer to section 7.2 and 7.4. 7.2 gives you the properties of parallelograms. 7.4 gives you the properties of special parallelograms. Your special parallelograms, there's 3 of those. That is your square, rhombus, and rectangle. So you got to familiarize yourself with the properties of rectangles. That means for a rectangle, all 5 properties of parallelograms apply, plus one that is specific to rectangles, apart from the definition of what a rectangle is itself. So again, if any one of these options applies to all parallelograms, then that's probably not it. You want to look for which one of these is specific to rectangles. I'm going to leave it at that for question. Goodness gracious.